Hi, welcome to the Calculus 3 practice sections here. We are in the unit number 2, the partial derivative. And this is our assignment number 4 practice. So this assignment basically we talk about the tangent plane and the linear approximations. Okay, so we're going to work several problems in our worksheets. So to give you the ideas, how to we do those type of the things. Okay, so let's go to our assignment worksheets here. And we start to work on that. Okay, so, all right, so the first problems I'm going to do is problem number 6 here. So what do I want to find? They want to find the plane, the tangent plane to the given functions here, right? So in order to find the tangent plane, at the point 3, 1, and 0. So as we know, what do we do here? First, we take the partial derivative of x. So the partial derivative of x, natural log, this is x minus 2y. And then the chain rule, x is 1, right? Okay. Then the same way we do the partial derivative of the y is here is a chain, so it's a natural log, derivative is put in the denominator. Then the chain rule x minus 2y to y, so what I have here, negative 2, see here. Then after that, I need to find the the substitute the point, right? So it's 3, 1. So f of x is 3, 1. If you put the x equal to 3, y equal to 1, you will get 1. Then this is the f of the y, 3, 1. The same thing, 3, 1, you will get a negative 2, see here. And this is our point, x0, y0, z0, right? So our tangent plane will be equal to what? Will be equal to z minus z0, so it's equal to 0, it's equal to f of x, so it's 1 times x minus x0, so x minus 3 plus negative 2, y minus y0, so it's y minus 1 here, right? So if you just simplify a little bit, you will get z is equal to x minus 2y and minus 1. Okay, so it's pretty straightforward here, okay? Okay, so now the next set is, they said explain why the function is differentiable at the given point. Then find the linear approximation for the functions here. Okay, so let me give a little bit more space here so we can work on that, okay? All right, so now we're going to work on the number 16 here, okay? So the first thing is here, so we say, okay, so in order to find the linear approximation, so we're going to take a what? The derivative of the partial derivative is f of x. So y is a constant. So what is sine x here is cosine xy, right? And then the chain rule of x, so it's what is 1 over y here, right? Now I need to do the partial derivative for the y. The partial derivative of y, this is 1 plus. The same way, the sine the y will be cosine x of y. And then the chain rule of x of y. So what is here is negative x to the y what? To the y squares, right? Okay. So that is then we plug the number in here. So plug our point. So x0, 3. Okay, so if you plug the x equal to 0, y equal to 3, and you will get 1/3 here. And the same way is here, this is y, you plug in the 0, 3, and you will get the x equal to 0, so you will get 1 here, all right? And then also, and so here, because the problem says y is differentiable. So the reason why is differentiable, because if you take a look at the f of x and the f of the y, they are both what are the continuous function except at y equal to 0, right? So we know the f of x and the f of the y, they are continuous, right? Except right? Except for they are continuous for everything for y is not equal to 0. So I know f of xy is differentiable, right? So this one is differentiable at 0, 3 here. Okay, so now what is our linear approximations here? Okay, the linear approximation will be very similar to what? F of what? 0, 3, right? So when you put the 0, 3 here, so like if f of the 0, 3, x equal to 0, y equal to 3, so this will be 3, right? Okay, and then now in here the f of xy, so we say it's f of 0, 3 plus the partial derivative of x at 0, 3, then the x minus what? Minus 0, then plus f of the y at 0, 3, then y minus what? Y minus 3, right? So f of 0, 3, so I know the linear approximations here, it will be 3 plus 0, 3 x is 1/3 of the x's here, right? So it will be the 1/3 of the x, and what is here? So it's 1, right? Plus y here, okay? So that is what we find the linearization for the, the Lx here. Okay, so those are pretty straightforward. Let's take a look at another ones here. So let's say, hey, try to find the linear approximation and to verify that this is the correct linear approximation at 0, 0, right? So let's say to verify this is correct. Let's see here, right? So let's say here, so if this is my f of xy, so the f of 0, 0 is what? It's -1, right? Okay, so now let's do the same ways here. So the partial derivative of x. So what is the partial derivative of x? Quotient rules, right? So it's x plus 1 to the square, then hold it so minus the top is 0, so then you hold the top, so minus y minus 1. Take the derivative of the bottom is 1, right? Okay, so this ones here will give me what here? So this is x plus 1 to the square, so this is 1 minus 1. Right? Okay, so then to do the same way for the partial derivative for the y, because the x is a constant, so this will just be x plus 1 to the y. Now I plug in the 0, 0. So when x equal to 0, y equal to 0, what is this ones here? I have 0. And the f of y, you put a 0, 0. What is here? Oh, it's 0 over 1, so it's zeros, right? Okay, so I did not do the derivative correctly. So the partial derivative of the y, so I need to take the derivative of y, so it's 1, right? So it's here. So the same way is here. So it's 1 here, right? Okay, so it's 1, all right? So it's 1. Okay, so now I can use my linear approximations, right? So the linear approximations will be equal to what? F of the 0, 0 plus f of the x, x minus 0 times x minus 0 plus f of the y times y minus 0. So I know the 0, 0, we just plug in is -1. So plus x minus 0 is 0 plus y, 1 times y. So we've matched, right? So I know this, for this function, I can use this linear approximation, try to match it. Okay, so that's pretty straightforward. And okay, so now let's take a look at the next ones here. Okay, so the next ones here I'm going to do is number 30, and this one is just try to refresh your memory. So we want to find the differential, right? So that means I'm looking for the DLs, right? So that means I'm looking for the DL. And now this is R4. I have 1, 2, 3, 3 variables here. So let's try to see here. So remember the DL will be equal to what? The partial derivative dx plus what? Partial derivative dy and the partial derivative dz's, right? Okay, so let's try to see. I need to have a little bit more space here. So this is dl. So take the derivative of x, everywhere else. So x is here. So this is z to the negative y squared minus z squared dx, right? Okay, then minus y plus, right, plus dy. So xz is a constant. So that would be the xz and, okay, so this is xz. Okay, so this is xz e to the negative y squared minus x squared, then negative 2y, right? Don't forget the what? Don't forget the chain roots, right? And then this is dy's, right? And then plus the z. Now in here, be careful, I have a z in here, I have a z in here. So what I need to do, I need to do the product rule, right? So I have that this is x and e to the negative y squared minus z squared, then plus xz e to the y squared z squared, then negative 2z. And don't forget the dz's, right? So if you combine a little bit, so this one's here will be z e to the negative y squared minus z squared dx. Then this one can be negative 2xy, right? So this is the negative 2xyz e to the negative y squared minus z squared. This is z, right? So these ones here, here, okay, so this one's, xyz, okay, so this is e squared minus y squared dy, then plus the dz. Okay, so dz, I can factor this one, y squared minus z squared. Then here I have x, right? Okay, so I have x and then, all right, minus 2xz, what? 2xz squared, dz. All right, so I got it, right? So I hope I did not make any mistake here. So this is dx, dy, dz. So this one is pretty straightforward. It's just try to, use your, the derivative skills here. Okay, so now let's take a look at number 32 here. Let me give a little bit of space for number 32. Okay, so the 32s here, they say, I'm going to the z functions is x squared minus xy plus 3y squared, change from the 3 to negative 1 to 2.96 here. From the 3 to 2.96 here, right? Okay, so I want to compare the value of delta z and dz. Okay, so the first, let's try to write it 3 to 2.96. So the dx equal to the delta x is equal to what? Is negative 0.04, correct? Right. And the y, the dy is equal to delta y. So from negative 1 to the negative 0.95, so I add 0.05 here. All right, then now in here, let's take a look here. So I need to do the partial derivative of x. So it will be the 2x minus y. All right, and then I do the partial derivative of the y. It's negative x plus 6y. Okay, and so now I can plug the numbers here. So this is f of x 3 to the negative 1. So is 7th, right? And then this is f of x, f of y, 3 to the negative 1. What is 3 to negative 1? So it's negative 3, negative 6, so it's negative 9 here. All right, so now I can, okay, so in here, so now I can see the dz. So remember the dz is f of x dx plus f of y dy, right? Okay, so the dz will be 7 times negative 0.04 plus, right? So it's negative 9 times the 0.05 here. So it will give me the negative 0.073 here. Okay, now the delta z here is really you just plug in the true numbers. So this is 2.96, 0.95, negative 0.95 minus f of 3 and negative 1. So if you plug this number, so that means this is the x equal to, so this will be your x number, and this will be what, negative here. This will be your y number. You plug that one back to your functions, right? Okay, so you plug into the calculator, and I got this one is negative 0.71a. I got this is 71a29, right? So if you use approximations here, you got a negative 0.73, and this is your true value is negative 0.71829. It's really pretty close, right? It's pretty cool, right? Okay, now the last problem I'm going to do is the application problem. Like I said, this type of the problem have a lot of application problem in the real life, and let me give more space for these problems here. Okay, so these ones tell us, okay, so this one say the wind chill index is modeled by the functions here. T is the temperature, V is the wind speed, is kilometer per hour. The wind speed is 26 kilometer per hour. That means this number is V. With the arrow is plus minus 2 kilometer. The temperature, that means it's negative 11 degrees C. So this is T with a possible arrow plus minus 1 degrees here. Okay, so I know from the given problems, add the V is 26. T is equal to the negative 11. So what is this plus minus 2 kilometer? That means the delta V is less than equal to what? Be 2, right? That means it could be, could be plus 2 kilometer or could be minus 2 kilometer. So the same way is here, what is this plus minus 1 degree? That means the delta T could be less than 1 here. So now I want to calculate what is the maximum error. So that's why I say, what is the maximum error when I calculate the W, all right? So now let's take a look. So the W is here. So basically I want to find what? I want to estimate delta W. And I know that delta W can be estimated by what? Can be estimated by what? Can be estimated by the dWs, right? And I know what is the dW, right? So the dW will be equal to what? Will be, the W, you take the partial derivative for T, dt, plus the W, you take the partial derivative for V, dVs here. All right? Okay, so now let's take a look at the derivatives here. The wind by the t's, right? So wind by the t. So this is a constant. So I have, this is a 0.6215. Then in this one become constant. Then this term, the last term has a t. So when you take the derivative, it will be plus 0.3965. T disappear, but the V still there, right? It's a 0.16. What is this here? The whole thing, this is dt, correct? Okay, now I'm doing the v's, right? Okay, so for the v's here, and then plus, the first term disappears, second term disappears. So the third term, this will be a negative 11.37 V, so you use a power rule, so it's 0.16. Then V is here is 0.16 minus 1, right? Okay, so then the plus 0.3965t, and then you take derivative of the 6965t, right? 39, okay, and then take derivative of V again. So it's a 0.16 V, the 0.16 minus 1. All right. And then what you do here, so the maximum arrow, so you just substitute, right? So you substitute the V is equal to 26, T is equal to negative 11, and then the dt, you can substitute is 1, and the dv is equal to what? Equal to 2. So you substitute everything back there, and I got it is the dw is very close to the point of what? 0.96 here. Okay, so the 0.96 here. That means the delta W is can be estimated by the 0.96. That means my wind shear index, the maximum error going to be 0.96 kilometer per hour. That means when I'm measuring the wind chill index, sometimes could be plus like 1, plus basically so 0.96 plus minus 1 kilometer per hour. So I can estimate a little bit more or a little bit less, right? Because due to my measurement error from the wind speed and the temperatures there. Okay, that's it. That is for this assignment. Is pretty, I think this is a very easy assignment. Is a very, very mechanical, right? So you just plug into the linear approximation formula and the differential formula, right? So that's it. And I hope that you have I hope that we did a few problems here. Let's help you to finish this assignment. Okay, have a nice day here. All right, bye.